In this video, we will continue our discussion of continuous functions, specifically looking at two properties. So the first, what types of functions that we have encountered are continuous? And it turns out that all polynomials, rational functions, which we recall as a polynomial over a polynomial, trig functions, absolute value functions, and root functions, such as square roots, cube roots, etc., are all continuous wherever they are defined. Additionally, if you have two continuous functions, let's say f and g, and they are continuous at a point, then a constant times a continuous function is continuous, a sum or difference of continuous functions is continuous, a product or difference, or quotient of continuous functions is continuous as long as you're not dividing by 0. Raising a continuous function to an nth power or taking a square root will also be a continuous function as long as that square root is defined. So taking any of the continuous functions that we've encountered and combining them in a reasonable manner will give you another continuous function. So let's investigate the following example. The function given by f of x equals x squared minus 4 over x minus 2 is undefined at a single point, and the question is, how should it be defined in order to make the function continuous at that point? Well, the function that we have is x squared minus 4 over x minus 2. It's a rational function, and it will be continuous everywhere that it is defined. And the only place we have an issue with it being defined is where that denominator is 0. So this is undefined at x equals 2. So the question is, how should we define this function at x equals 2 in order to make it continuous? Well, at x equals 2, what we would need is that f of 2 would be the limit as x approaches 2 of our function. Now, unfortunately, we cannot simply just plug in 2 because that results in the denominator being 0. So instead, we need to do algebraic manipulations before applying our limit laws. And the algebraic simplification that is present here is that the numerator is a difference of squares. So it factors conveniently as x minus 2 times x plus 2. So the x minus 2's, which are present in the top and the bottom, cancel. What we are left with is the limit of a polynomial. So by the substitution property, we can simply plug in x equals 2, and the value of our limit will be 4. So what this is telling us is that if we would like to make a function such as f of x here continuous at 2, it needs to be 4. So if we define the new function f of x, now I'll use big F of x, to be x squared minus 4 over x minus 2 when x is not equal to 2, and 4 when x is equal to 2, this function will be continuous everywhere, but specifically in terms of this problem, it will be continuous at x equals 2. So another very similar problem. Now if we look at the function g of x equals sine x over x, it is undefined at a point. How should it be defined there in order to make the function g continuous at that point? So the function that we have, sine x over x, is undefined at one point, and that would be where we're dividing by 0. Now, in order to make it continuous there, we would have to define g of 0 to be the limit as x approaches 0 of our function. And this would just be going back to the definition of continuity at a point. And this is a special trigonometric limit that we encountered in a previous video. Its value is simply 1. So x equals 0 is the point where the function is undefined. In order to make the function continuous at that point, we have to define it to be 1. And what this is telling us is if we define the function big G of x, which is sine x over x when x is not 0, and 1 when x is equal to 0, this function will be continuous everywhere but specifically in terms of this problem, it's continuous at x equals 0. Another type of problem we could encounter is for a given function, in this example 1 over the square root of 4 minus x squared, determine at what point, if any, the function is discontinuous. So what we have to recall is that the function that we're given here is a polynomial 1. Polynomials are continuous everywhere. Divide it by the square root of 4 minus x squared. So the individual parts of this, the 1, the 4 minus x squared, and the square root of 4 minus x squared. Individually, these things are all continuous, so we just need to think about where they are defined. And the only issues that we are going to have is that the 4 minus x squared, well, first of all, it's in a square root. And we cannot have a negative number inside the square root. So we will say discontinuous when 4 minus x squared is negative, because we cannot take the square root of a negative number. Additionally, that 4 minus x squared sits in the denominator, so it cannot be 0. So we need to know where is 4 minus x squared bigger than or equal to 0. Well, this is a problem from chapter 0. It's an inequality. And how we have to approach this inequality is think about the zeros on the left. This factors as 2 minus x, 2 plus x. And to determine where this quantity is less than or equal to 0, we create a number line and a sign chart. So 2 minus x, 2 plus x is equal to 0 at minus 2 and 2. And the function 4 minus x squared is going to be entirely positive or entirely negative in each of these three intervals. So we need to check test points. In between minus 2 and 2 is 0. Less than minus 2 would maybe be minus 3. Above 2 would be 3. So if we use the sample point x equals 0, and we plug that in, we'll have 2 minus 0 times 2 plus 0, which is positive. So between minus 2 and 2, our expression is entirely positive. At x equals 3, if we plug that in, we're going to have 2 minus 3 times 2 plus 3. 2 minus 3 is negative, 2 plus 3 is positive. A negative times a positive is negative. So it's negative when we're larger than 2. If we plug in our sample point x equals minus 3, we are going to end up with 2 minus a minus 3, so 2 plus 3 times 2 minus 3, which is exactly what we have above, a plus and a negative, is less than 0, and we're negative to the left of minus 2. So we said the function will be discontinuous when 4 minus x squared is less than or equal to 0, and the sign chart that we've created to the right here indicates that that happens precisely when we're from minus infinity up to and including minus 2, or if we're at 2 to infinity. So the function will be discontinuous at the following points. So a similar question, but now for the piecewise defined function given here. Now the key observation to make, even though it's a piecewise defined function, which makes it look a bit scarier than our previous examples, is that when x is less than or equal to 0, it's a polynomial. Between 0 and 2, it's a polynomial. And when x is bigger than 2, it's a polynomial. And polynomials are continuous everywhere. So if I think about a number line in terms of this function with inputs to the left of 0, we're a polynomial and the function will be continuous. Between 0 and 2, it's a polynomial, which will be continuous. And larger than 2, it's a polynomial, which will be continuous. So the only points that we have to worry about are these connecting points. And by connecting points, I mean where the piecewise defined function changes from one function, say 1 plus x squared, to 2 minus x at 0, and then similarly at 2. So let's see what happens at x equals 0. In order for the function to be continuous, we need to know what is the function value and what is the limit as x approaches 0 of the function. In terms of the function value f of 0, we would use the first function, 1 plus 0 squared, which equals 1. In terms of evaluating the limit at 0, the function is defined to be one thing to the left of 0, another thing to the right. And that's an indicator that we need to use one-sided limits. So if we approach 0 from the left of our function, to the left of 0, the function is defined to be 1 plus x squared. 1 plus x squared is a polynomial, so by the substitution property, the value of this limit is 1. Similarly, if we take or look at the limit as x approaches 0 from the right, to the right of 0, the function is defined as 2 minus x. So this is the limit as x approaches 0 from the right of 2 minus x, which is also a polynomial. So by the substitution property, we can just substitute in x equals 0, and the value of the limit is 2. 1 is not equal to 2, so the limit as x approaches 0 of our function does not exist. And by the definition of continuity, if the limit as you approach 0 of the function does not exist, this is telling us that our function f is discontinuous at x equals 0. So discontinuous at x equals 0. Now we need to go on and check the point at 2. So at this point I've included a graph of the function. So looking at the graph, we can hopefully very clearly see that at x equals 0, the limit is not going to exist because it's the one thing from the left, the second thing from the right, so the function will be discontinuous. So let's check at 2, and hopefully as we can see from the graph, the function is going to be continuous at 2. So f of 2 is going to be 2 minus 2, which is 0. And in order to determine the limit as we approach 2, we need to take the limit from the left and the limit from the right. As you approach 2 from the left, the function is defined as being 2 minus x. 2 minus x is a polynomial, so by the substitution property, the value of this limit is 2 minus 2, which is 0. Likewise, if we take the limit as we approach 2 from the right, our function is now defined as x minus 2 quantity squared, which is a polynomial. So by the substitution property, we can just substitute in x equals 2. 2 minus 2 quantity squared is also 0. The limit from the left is 0. The limit from the right is 0, which tells us the limit as we approach 2 is equal to 0, which we've also seen is the function value. So the function is continuous at x equals 2. So in the beginning, our observation is the only 2 points that we would have to worry about continuity are these connecting points, 0 and 2. We've seen that the function is continuous at 2 and discontinuous at 0. So the final answer here would be discontinuous at x equals 0.